So the absolute simplest piece of optics that we build is typically a mirror. So there's a mirror, it's got a silvered surface, and here's us. Now if we point our eyes in the direction of that mirror, the light that's reaching our eyes is going to be bouncing off our mirror at a particular angle. And we know that the angle that it bounces off the mirror is going to be the same as the angle it came into the mirror on. So if I've got light that's got to get from my feet up to my eyes through the mirror, then I know that's got to get exactly halfway up to the mirror and then exactly the same distance back up to my eyes. And I haven't drawn this perfectly, but we know that reflection means that this angle, the angle of incidence, and this angle, the angle of reflection, are the same. And if those two angles are the same, if I consider this triangle here, sort of the mirror up to the eyes, and the triangle that goes from the mirror down to the feet, then those two triangles, because they share that same length in the middle, and because those two angles are the same, that means those two triangles are exactly the same shape, just mirror reversed. And that's why it's equal distances from the feet up to the mirror as it is from the mirror up to the eyes. And exactly the same thing happens when you consider the light reaching from the top of the head to the eyes. Now the eyes think that light just traveling as it normally does in straight lines, and so it thinks that those feet came from this direction and that they were about that far away from various other clues. And they think that the top of the head came from this direction and is about that far away, and so on for each other part of the body. And so the eyes see something over here. And that's why we see an image inside the mirror. It looks as though it's actually coming from a room and a person inside that mirror. And this is called a virtual image. Now, if you want to find out exactly where that image is for a flat mirror, you just draw those light rays like that, and you do some geometry. We note that the angle over here is exactly the same as the angle over here, because that's just a straight line. And therefore, we can tell that this triangle here and this triangle here must be just copies of each other, except upside down. So then we can tell that image basically looks exactly the same height as us. We know that this height, the height of our object, which in this case is us, and the height of our image is the same. So those two heights are the same. And we also know that the distance between the mirror and our object is the same as the distance between the mirror and our image. So flat mirrors are pretty simple. Well, how do we work out something like a curved mirror? Well, once again, all we have to do is work out how the light gets to our eyes. So we know that the angle that it reaches the mirror is exactly the angle it comes off the mirror. So we can see light will bounce there, reflect off to our eyes, and light coming off the top of our head to do something like that. And then our eyes just think the light travels in straight lines, and so it looks like there's someone back here. It looks like there's someone with feet back here. So what we've got there is another virtual image, but you'll see it's magnified. And if you do exactly the same thing with the mirror curve the other way, you'll see you get a virtual image where the image is smaller than the person. And we can figure out how much bigger that image has to be by figuring out where it is. Because we know that that image is not distorted, then they're going to be in proportion. So the distance here, which is the distance between the object and the mirror, and the distance here is going to be the distance between the image and the mirror. Then the magnification is going to be simply the ratio of those. So if there's an undistorted image that looks further away, it has to look bigger. And if I'm exactly the same distance away, then I'll be the normal size. And if I'm closer in the image, if I'm close to the mirror, then I have to look smaller. Now, fairly obviously, whether or not you get an undistorted image depends a lot on how the mirror is curved. If this mirror was really wobbly like that, then obviously we wouldn't get a clear image inside that mirror. And also it depends on exactly how that curve is done as to whether we get a stretched image or a distorted one or not. Now the kind of mirrors that give you nice and clean images are ones that bring parallel lines to a focus. And again, it's very easy to make a piece of optics that doesn't have a well-defined focus, but a lot of mirrors are made that way so that all parallel rays all go through the same point. It turns out that the position of an image depends very much on exactly where the object is compared to that focal point. So if we put the focal point a distance f away from the mirror, then we get different images depending on whether we put our object inside the focus or outside the focus. And the way we work out where those images go is that we consider rays that go through the focus and parallel rays. So if we have a ray that comes in parallel from the top of the head, then we know where that's going to go. It's going to bounce through the focus. And because light travels backwards exactly the same way it travels forwards, if we had a ray that came through the focus, it would come out parallel in this way. And so the other ray we can look at that goes through the top of the head is the one that comes as though it's coming from the focus, and then we know that that will go out parallel. So if it were coming from the focus, we know that it would then come out parallel. And then of course, both of those seem to be coming from this point way back here. And so we have our virtual image. And so if that is the distance from our mirror to our object, and this is the distance to our image, then it's really just a matter of geometry to link these three distances and figure out exactly how far away the image should be if you know the distance of the object and the focal length. And if you know those two distances, then you also know the magnification just from there. Now we find that the image works really quite differently for the person who's outside the focus, and we can draw this much better on this size diagram if I make this person bigger, a little less clumsy. But we just follow the same rules. So a light ray that goes through the focus comes out parallel. And a light ray that comes in parallel goes through the focus. And what you'll see is that the light rays, if we keep on going further here, the light rays seem to be coming not from a point on the other side of the mirror, but from a point on this side of the mirror. And indeed, this is what we call a real image. Because if you're looking at the image of that head, it's not just that it appears to be coming from this point, the light is actually coming from this point. If you look over at the virtual image, the light appears to be coming from that point, but actually it's coming just from the mirror. You'll note also that the real image in this case is inverted, and so you can end up with upside down images. And you can always figure out exactly where the image is, how big it is, whether it's real or virtual, by following the simple rules of following where the light rays go. And when you have something that has a focus, you just do the rays through the focus and the parallel ones, and when you don't, you just have to carefully draw them as they bounce off the mirror.